All right, welcome. In this video, we're going to be talking about logistic growth. So in the last section, at the very end of the last section, we talked about two things. We talked about the need for a logistic model when there's an exponential growth, but there's some kind of limiting factor, which is the more realistic exponential growth in the real world. Um, and then we also talked about how to solve the differential equation for logistic growth and go from the dy dt to a y equals equation that is going to have y in terms of t. So at the top of our notes here, we've got both of those. We've got the differential dy dt equals ky times big L minus y. And then we've got the equation solved for y, all right? The particular, or the general solution where we've got unknown L, C, and K values that when we get a particular solution they're all gonna be number values. All right, we've also got this visual over here. Just a reminder of what a logistic graph looks like. It's gonna be important for visualizing some of these problems where we've got the upper bound that's a horizontal asymptote. That's gonna be y equals L, that numerator. And then the lower bound is going to be y equals 0. So this is one of those few bounded functions where it's bounded above and below. There's also the inflection point, which is going to be where, again, it changes from acceleration increasing to acceleration decreasing, right? So that second derivative changes sign there. It's still, the function itself is increasing over time always. But that inflection point is going to be right there. We're going to talk more about that in just a second. All right, so to help you remember this function, y equals L over 1 plus C e to the negative LKT, think lice minus licht. So L1 is I, C, E, and then to the minus licht, because you're going to need to know this function. All right, and it's slightly different than probably the logistic function form that you learned in pre-calculus or maybe math 3. All right, so notice the prominence of the carrying capacity value L in the form of the equation. This is very important, especially when asked for the limit as t approaches infinity, or when asked to find the y value when the y values are increasing most rapidly. In other words, the inflection value. All right, so not only does acceleration sign change at that point, that's also the point where it's the steepest, which occurs at half the carrying capacity. So here's another important piece of info about that inflection point. It always happens halfway up from 0 to the carrying capacity. All right, so there's a couple of different types of questions that can be asked about these logistics, and we're going to look at a couple of those examples. All right, first one says the population of Alaska from 1900 to 2000 can be modeled by the following logistic equation. All right, they give us P of T, this specific equation. It's got the L, the C, the K, all solved for, right? Notice it's already in the form that we're looking for. This 1 plus is really important. This exponential piece in the bottom is important, and then the single constant in the top. Those are all needed to be in this form here. Okay, so we can see the L is that numerator. So right away we can say the carrying capacity is at 895,598. Our C value is at 71.57. And then this is the product of the opposite of L and K. So we could find K from that if we needed to. For example, if we needed to go back to the differential equation for some reason. It tells us that P is the population T years after 1900. So that's kind of our 0 there. T equals 0, corresponding to the year 1900. All right, A says, what is the predicted population of Alaska in 2020? So they give us a time. Think about that as giving us an X value. They want us to find population. That's our Y value. So we're just plugging it in. But you got to be careful because we got to convert that into terms of T. So 2020 is 120 years since 1900. So 120 is what we want to plug into P. This whole section, can't remember if I said this at the beginning or not, is calculator active. All right, so you're expected to use your calculator on these problems. All right, so plug in 120. I would put this into Y1 right away, and then say Y1 of 120, or go to your table and go to 120. All right, it's going to give us that value again. You should expect a value less than this carrying capacity. If you get something bigger, double check your work. All right, that's as high as it should get. B, how fast was the population of Alaska changing in 1920, 1940, and 1999? All right, how fast was the population changing? That's a rate question. So we need to look at the rate. So we need to look at essentially P prime. If we were given the dy dt, we could just plug it into that. But since we're given this and we have our calculators, we're looking at the derivative at specific points. So take advantage of nderive in your calculator and just say P prime of 20, P prime of 40. Again, years since 1900. Don't put in 1940. You're going to get numbers really close to this if you put in the actual date. And then P prime of 99 for 1999. All right, and you should see those values. No, check that. You shouldn't get a number close to that. That's the actual population. But you should see the rate changing, and it actually kind of flatten out. It'll minimize as you get, if you're plugging in actually thousands of years in the future. It should approach zero. Okay. So we can see the rate changes quite a bit between 1920 at 1,678 people per year versus 99 of 9,741 people per year. All right, it's a big difference. All right, part C. All right, lots of parts to this one. When was the population of Alaska growing the fastest? What was the population then? Again, fastest growth rate, what we just set up here, is at half the carrying capacity, is at the inflection value. That's when the slope is the steepest. So we need to find that value. So half of L is 447,799. So we need to know when does our graph hit that height. All right, that's going to be our inflection point. That's going to be when, if we can find that t value. So set your equations equal to each other. For me, I've already got P of t and y1. I would just say y2 equals that and find where they intersect. All right, again, you're looking for the y value, reinterpret it in terms of the problem. So when you write your complete sentence answer, make sure that you give that actual date as opposed to just it happens at 82. All right, D. What information does the equation tell us about the population of Alaska in the long run? All right, think about the long run is as years go on and on and on without bounds. So as t approaches infinity, so you're looking at a limit. You don't have to actually evaluate the limit, but know that, again, as those t values go on and on, this is an upper asymptote here. It's never going to get above that. That asymptote is always going to be y equals that numerator, okay, that carrying capacity, that L value. Okay, so it's going to max out, okay, or you can say it's going to approach that amount of people without going over. Okay, part E. When P is less than 447,799, what is the sign of dP and second derivative dP dt? All right, what does this mean in the context of the problem? Okay, so the population is always increasing in a logistic function like this, unless we're looking at cases that we'll look at in the next page where our starting population is above the carrying capacity, which is rare, but something you'll look at if you take a differential equations class in your college education future. It's going to be increasing, right? All where our function is defined. Up until that inflection point, the second derivative, again, think about that as acceleration, the change in the rate is also increasing. It's getting steeper, right? It's increasing at an increasing rate is what the population is doing, right? Part F, when the population is bigger than that, then the population is still increasing, right? It's still getting bigger, bit closer and closer to that upper asymptote, but now it's at a decreasing rate, all right? The slope is flattening out over time. Okay, so the population is increasing at a decreasing rate. All right, we'll tackle page 2 in the next part of this video.